Hello everyone, welcome to my video on implicit differentiation. Thanks so much for joining me. As I say probably at the start of every one of my videos, I'm Darren from Maths Guru. Really good to meet you. Are you well? Yep, I'm sitting here literally expecting a response, so let's move on before you switch off. Behind me, you will see our learning objectives, and we're going to understand what an implicit equation is, or an implicit function, and understand how to do implicit differentiation. This stuff is amazing, okay? And it comes up in the VCE exam every single year. Thank you very much, VCAA. We love you because this is the type of stuff you just learn, you know how it works, and you're like, okay, I can do this. This is great, okay? Now, recap of past learning. Basically, it's important to know that a circle is an example of what we call an implicit function. Now, that means it's written in terms of both the dependent and independent variables. And a great example is this one here, x squared plus y squared equals 1. Okay, that's basically a circle. We know that that's a circle. In fact, it's the unit circle because it has a radius of 1. All right, so now if we try and express this basically in the form of y equals f of x, or x equals a function of y, we actually can't, because realistically speaking, they're not functions. If we were to draw the unit circle, and let's draw a pretty circle through here, and try and remember that for it to be a function, it has to pass the vertical line test. There we go. There's my vertical line test, and it's going through twice. Now, what does that mean to me? Why does that matter in any way, shape, or form? Well, when we are differentiating, what are we trying to do? We're trying to find the gradient at a particular point. Now, example, if this was our x value of a point of a half, what are we actually going to end up finding? Well, if we were able to differentiate that function, which we can't, we're going to end up, or rather, if we're going to try and differentiate it, we're going to end up with, well, two equations. Because ultimately at that point there's going to be a gradient here, and there's going to be a gradient there. Now, that makes life very complicated. And so it would be great if there was an alternative way of doing this. All right, so we've already met in a previous video how to do a question like this, where we've got x is equal to y cubed. Now, if we wanted to, we could say, well, y becomes equal to the cube root of x, or we can write that as x to the power of a third, which becomes 1/3 x to the minus 2/3, which becomes 1 on 3 lots of, well, the cube root of x squared and cube, for example, which looks absolutely disgusting if I ask you. Alternatively, we said, well, we now know that actually we could do dx by dy becomes equal to 3y squared. So we differentiate both sides with respect to y. And then we knew that basically dy by dx was the same as 1 on dx by dy. Oh, okay. So in which case we know that dy by dx is equal to 1 on 3y squared. Oh, well, hold on a moment. We have a small issue here as well, because dy by dx in this situation has to be given in terms of a y value. Now, I don't actually think that's too much of a problem, because we know in this situation here that if I was, for example, given an x value, I could quite easily find a y value by substituting it into that equation there. Okay, and I don't like that orange, so let's highlight it in yellow. There are ways around this. But we sort of said in a previous video that having it in terms of y could be really, really useful, right? And you're going to turn around and say, well, is it possible? How to go from here to here? Well, remember, we could work out what y squared is by basically cube rooting both sides and then squaring it if we wanted to. And what you will find out is these things here are actually exactly the same thing. Now, I'm going to show you the theory behind implicit differentiation, but then I'm going to show you the shortcut in just a moment, because it really is just pretty funky. And I always tend to remember the shortcut more than anything else. Right. So let's go back to the equation that we had a moment ago that was x is equal to y cubed. And what I'm going to do is I'm going to differentiate both sides of that equation with respect to x. Okay, so rewriting it here, d by dx of x, just differentiating that with respect to x, d by dx of y cubed. Now, you're going to turn around and say, well, hold on a moment, I can't do that because I can't differentiate y cubed with respect to x because it hasn't got an x in it. Okay, so let's use a bit of a chain rule trick that we've sort of known before. Let's say that y is now going to be equal, u is going to be equal to y cubed. Now, using the idea of the chain rule, therefore, du by dx, if I differentiate this with respect to x, du by dx is exactly the same as du by dy times dy by dx. Now, I know there's a lot of letters being thrown here at the moment, but ultimately, if you remember, that if I've got du by dx, I can write my du on the top there, multiplied by my dx on the bottom there, and I can choose whatever differential I have up there. Now, because we've got respect to y, I'm going to do dy there, right? So those are exactly the same. Now, the reason this becomes helpful to me is because I've got u and y, all right? I can differentiate u with respect to y because we've said that here. All right, well, let's do that then. So that's basically what this is saying here. So du by dy becomes 3y squared. Oh, okay then. So substituting that in, that becomes 3y squared times, I don't know what dy by dx is, so I'm going to leave it by dy by dx. That is my du by dx. Okay, right, well now if we go back to having this here, right, the differential of x with respect to x is basically 1. And the differential of y cubed with respect to x, so again, let's just go back to here, that's du by dx. If we write it out the long way, that's the d of y cubed with respect to x is now 3y squared times dy by dx. So where I see d y cubed by dx, I can write that as 3y squared by dx, which again, all I've done is substituted it into here. Well, if I want dy by dx, then I divide both sides by 3y squared, and there we go. All right, now you're going to turn around and say, that was so long. It was, but look what seems to have happened. All right, and this is the shortcut. This is the bit that I'm like, oh, this stuff is amazing because there is a shortcut that actually works every